Hello class, welcome to this week's lecture where we will talk about how to leverage convolution in neural networks to deal with image prediction tasks. So over the last few weeks during this course, we've built up from very simple techniques how to store data, how to visualize it, how to represent it in feature vectors, how do we deal with text, how do we feed all this text in traditional classification and regression techniques. When do we choose what type of model? Hybrid models seem to perform better. Sometimes we need a comprehensible model though, so this is a balance we need to take into account. And now these last few weeks we've moved more into the domain that has been under heavy development the last 5 to 10 years, which is neural networks and more specifically deep neural networks. While we've talked about word embeddings, how to represent text, this week is going to handle more about how to represent multidimensional data. And this means images, even videos, although we're not going to be practicing that, time series. How do we deal with input in which the representations and the relationships within the representation are important? For that, we use convolutional neural networks. So convolutional neural networks really's first application was images representation. So let's have a look at how do we represent images. So as I mentioned, we've dealt with simple numbers, time series, text, but how really do we represent images? So when we have these convolutional neural networks, this will enable us to do some computer vision tasks. What kind of tasks are there in computer vision? Because if I say computer vision, really it means to represent images and videos on a computer. These days, the field implies that you're using neural networks, but that's really not always the case. Some of the tasks related to data science that they do is, let's say, image classification. This is the easiest one, let's say. Here, you want to know what the image is on the left. Okay, so we have a chair. Is this a chair or not? Then you want a slightly more complex task. We can do image classification and localizing. Okay, so here is an object and it is a chair. Object detection. Okay, there's an object. Here's a tree, here's a chair, etc. Okay, so multiple objects in one image. Then the last sort of the complex tasks in this is image segmentation, where you're going to be predicting a map that shows you where exactly the entire image is. So not just the bounding box, but the entire image map. And if you're interested in how this sort of prediction task looks like, is here our input will be the pixels of the image. Our output will be sort of a map. We call it a map. It can be a binary map, which means it's 0, 0, 0 if there's no chair, and it'll be 1, 1 where there is a chair. And that's sort of, if we color it and we overlay it over the original image, it will segment nicely where the chair is. So these kinds of binary masks, or if they're not binary, we refer to them as soft masks. That means they can be actual double numbers. Often you start in your training set to create binary masks, because in our original ground truth label we would know where the chair is, so we just put zeros and 1. And when we predict, one possible way is to get a probability for each pixel, is it a chair or not, so it will be a soft mask that you're actually generating. Okay, so you train on binary mask and you predict soft masks. All right, so image classification is very useful in the whole field of data science, and it just means classifying images into one or more categories. So we can also have multi-label classification, a little bit harder to evaluate. Well, because you can't use the standard cross-entropy loss, you have to think a little bit about how many categories do you allow. What if an image belongs to 2 categories in your data set, but your algorithm predicts a third? And how do you quantify how accurate this classification is. Okay, so there are some other strategies for multi-label classification. We're not going to be dealing with that right now. Training data must have images labeled with their class. So it can be hard to find a data set, but very often people use Mechanical Turk, for instance, which is a paid service by Amazon. There's other alternatives as well, to have volunteers label data. Okay. CAPTCHAs, you may not know this, but companies are actually using CAPTCHAs, the things that it used to be the numbers that you have to type in from the image before you can log on some site. They actually only evaluated half of the numbers you give in and used the other half to populate a data set. Okay. So that's due to your help now that we have big data sets. So there's a bunch of challenges in images. Okay, so we can have some of the challenges are depicted here, but also think of, in self-driving vehicles, we have, a photo of a street can look so many different ways. There could be a lot of object variation. It's raining, it's light, the sun is shining, it's cloudy, there's some tree shade covering the image. They can have different types of illumination. There can be an object half in front of an object. How do we deal with that? And there can be a bunch of background clutter. Just some of the examples of challenges in images. Okay. All right, so I should say that when we move into the domain of convolutional neural networks, we're going to be touching a lot on the area of deep learning. Okay. Why is that? Because really convolutional neural networks are part of what made deep learning possible. And we'll get to that when we start talking about Lynette and the first deep architectures in a little bit. Okay. While as a data scientist, right, obviously we have to keep our problem statement in mind. So it's important to keep thinking of things like challenges, image augmentation, not just the techniques and the technologies that you're implementing. That said, if you're a data scientist, you really can't imagine not knowing about convolutional neural networks or some basics of deep learning when choosing your model. Luckily, we have some tools that make it very easy for us to implement all of these convolutional neural networks, such as Keras, PyTorch, and the like. Fast AI, another example of how it's becoming more and more easy to implement these deep neural networks. Right, so deep learning with convolutional neural networks, or CNNs, convolutional neural networks, is really everywhere, right? So much of the information on the internet is being used, labeled to enable all sorts of models for speech recognition, image classification, etc. Okay. Also for language, which I think Prof. Sujanya will talk to you about, is it is possible to leverage 1D convolutional neural networks for speech and text representations. Okay. Actually, I'll talk a little bit about speech, but he'll talk about how to represent words with 1D convolution. We move to medicine. We can do X-ray analysis. I think I saw some data set on Kaggle about using X-rays, classify between COVID or non-COVID X-rays. Do cancer cell detection, all sorts of medical images. I'm honestly not really sure what's in this picture. Okay, if you know, let me know. Media and entertainment, of course, people examine what you're looking for, what you're looking at when you watch YouTube movies, when the kind of images you see, everything's being analyzed. In security or defense, there's a lot of face detection going on. Actually, even in media and entertainment, face detection is going on because there's some apps like if you're in a taxi, you're watching advertisements, it can do face detect. There's people developing apps to do face detection to see if you're happy with the app that's being played or not. Okay. And then there's autonomous vehicles. Obviously, there's a lot of computer vision happening, and CNNs are key in representing all these things. So when you know a little bit about AI, you know that the whole field, AI, deep learning, machine learning, it's all so related, right? And you know that AI actually was first developed in the 50s. Then after a while of being popular, it sort of hit neural networks, kind of got less popular until the invention of the perceptron. And then the connectionists sort of took over, and they were very interested in how we could use neural networks to represent the brain. Then sort of the 90s, 80s, not much going on again. These are referred to as the winters of AI. And what's really important for us is that somewhere in the early 2000s, we awoke from the last AI winter, and this was due to a number of factors. And these factors are not just important for AI, equally for data science, which I think are two very related fields. What we didn't have, in the 70s was a lot of data. So now we have data from the internet, we have big storage facilities, everybody has a ton of photos on their cell phone. So we have big data. Okay, we also have the means to process this big data. We have powerful graphical processing units, GPUs, and this is especially important in this class because GPUs are exactly what we leverage when we do convolutional neural networks, which imply doing a lot of matrix multiplications, which is exactly an operation done on the GPU. Okay. Then thirdly, what we have is some very important evolutions in the field of deep neural networks. More importantly, CNNs, which came about 10-ish years ago. Okay. And so this empowers us to do something with this big data on these powerful GPUs. Okay, so I'm not going to go into this with you again because I'm sure you see this in machine learning and earlier in this class as well. But neural networks basically represent the perceptron model, which whereby for each node you have a number of inputs and it goes through pointwise multiplication and an activation function. Okay, and it has enabled us to go one step further into convolutional neural networks. Okay. So when we have neural networks, what we do to go into deep neural networks is basically we stack multiple hidden layers. Okay. They can be of different sizes, and the premise is if you give enough training data, then the neural network can approximate very complex functions that map data, input layer, onto the output layer, okay, which are your predictions or your decisions. Okay. Now, you've all seen this person, I would assume, Yann LeCun, which is basically the founding father of convolutional neural networks, who's now chief AI scientist at Facebook. So we'll be talking about the name, you'll see the name LeCun or Yann come back later in this lecture, and I'll point out what are the things that he invented. Okay. So convolutional neural networks, as per Jan's definition, are a specialized kind of neural network for processing data that has a known grid-like topology. Okay, so this can include time series data, which is a 1D grid, so it can also be words or sentences. It can be image data, which is a 2D grid. It can even be videos, which is a 3D grid, but it's a little bit more complex. Okay. So convolutional neural networks have been tremendously successful in practical application, right? The name convolution comes because it employs a mathematical operation called a convolution. This is a type of linear operation that we'll be practicing later in this in the lecture. So we call a convolutional neural network one that uses at least one layer of these convolutional operations. Okay, so a CNN, you feed it an image and it will make a prediction, in this case a sentiment prediction. Okay. they are really everywhere. So some of these examples that I mentioned before, object detection, segmentation, which you see here again, all using CNNs. Okay. Now, there's some very interesting advances that allow us to put CNNs even in self-driving cars, because NVIDIA has been inventing these amazing GPUs. So we see a Tesla card here, which is a high-end card that we have in our lab servers, for instance. But NVIDIA has also created the Jetson cards, which are basically low-powered devices that can be plugged into IoT devices, which is pretty amazing. So it allows us to really tinker and make real products with GPU power. All right, here's another famous example. I believe this is the OpenPose library at the top here, which is doing deep learning for real-time pose estimation. So remember how you used to be able to use the Kinect, which has an infrared scanner, to get the depth information and the skeleton representation of yourself? Well, these days you can use something like OpenPose, which is a library based on CNNs, to estimate your joints and your skeleton. And it works pretty decently. There's some other examples here. At the bottom is a computer game that uses some offline Monte Carlo tree search planning, but the input is processed using convolutional neural networks. So it's really taking the screen as input. More examples. Again, for self-driving cars, we have the traffic signs. All right, the image at the bottom left is a rotation invariant convolutional neural network for galaxy morphology prediction. Okay, so measuring the morphological parameters of galaxies is a key requirement for studying their formation and evolution. So surveys such as the Sloan Digital Key Survey have resulted in the availability of very large collections of images, which have permitted population-wide analyses of galaxy morphologies. Okay. Usually this is done by visual examination by experts, but this is very time-consuming and does not scale well. Okay. So the Galaxy Zoo project applied a crowdsourcing approach to label a certain amount of images, and then from there they developed the CNN network. Here's another Kaggle challenge, which is on whale recognition from tons and tons of ocean data. Where are whales being spotted? This helps in the whale conservation project so that they can track their migration cycles and study some of their behavioral patterns. Right, so here's an example of image captioning, which is where you give an image to your neural network and then you try to predict this textual description of what is happening in the image. So on the left we have a perfectly errorless prediction: a white teddy bear sitting in the grass, a man riding a wave on top of a surfboard. Perfect. Some minor errors in the center: a man in a baseball uniform throwing a ball. Almost a very subtle difference. A cat sitting in a suitcase on the floor. It's not really a floor, but it's pretty good. Somewhat related: a woman is holding a cat in her hand. Okay. A woman standing on the beach holding a surfboard. Almost correct. Okay, so there's still some work to be done. Also, this is work from 2015. This is 5 years ago. But it's pretty solid work. And it's a very interesting task as well, not easy at all. Okay. Another application of CNNs is more in the generative models, which is something that we discuss in the AI class. It's not really for data science. But I want to mention it, that you can use CNNs to represent your images. What you do with it, what kind of complicated AI model you use with them, can be totally up to you. So here I think they use the Pix-to-Pix network, which is a type of generative adversarial network to do style transfer and transfer these photos into the style of a famous painter. Okay. All right, how does it work? First of all, let's have a look at how an image looks like. We usually have 3 layers in an image. It's basically a matrix of pixels, and it has 3 matrices of pixels, one for red, green, and blue. Okay. So this is represented in an image as 3 channels. These layers are called channels. And overlaying these three channels over one another gets you the actual image. So we're dealing with matrices of double numbers, double floating numbers. So how is a black and white image usually represented? For black and white, we don't have floating values. We only have zeros or one. And I'm so sorry, usually the ones is actually the light ones and the zero is the black. So I got that mixed up here, but I think you understand the gist. So before we had convolution, how does it work? I showed you the equation of the neural network. We have each pixel value basically an original value of a 24-bit color image. That means we have 8 bits per color, so 256 values per bit for each of the channels, means we have a total of 16 million colors that we can represent. Okay. So to pre-process the color values, usually we normalize everything between 0 and 1. Having something normalized in a neural network typically will increase your performance. Okay. So, before we go into how convolution works, how does it work in a normal neural network? So, when we take a color image, 300 by 300 pixels, okay, that's pretty tiny, right? That means we would have 300 by 300, the dimensions, times 3 channels, input values, which equals to 270,000 inputs, okay? So, one-dimensional vector here of length 270K is inputted in the network for a simple 300 by 300 image. Okay. So if we say we reduce the number of nodes in our first layer, we have 1,000 hidden nodes. So that means we reduce our data from 270,000 to 1,000 nodes divided by 270. Which is small. We need about 270 million parameters or weights to train in order to train the neural network with only this first layer, okay? Think about that, 270 million parameters to train one layer neural network with a tiny input image size. This becomes a high chance of overfitting because your network simply is too complex. Right, so what is the solution? Convolution. It drastically reduces the number of parameters that we need to learn, and this is key. So I want you to remember this. Convolution is way more efficient. You have way more weights to train, so that enables us to train much deeper networks. Okay. In addition, it preserves locality. So whenever you have dimensions and relations within your image to be learned, then this convolution will help you do that. So for instance, in this image here, these white things, they signify something, the fact that they occur together. So knowing that this pixel here is right next to a pixel there is important for the network, and that's something that you would lose if you were just to flatten the image into one dimension. Okay, so we're going to go into how a traditional, standard, not deep neural network, convolutional neural network looks like. So we have input images, notice 3 channels, red, green, blue. We start with a convolution with ReLU activation. I'll talk about that. And pooling, I'll talk about that. Then this is repeated in the most simple form. It's repeated once, but you can repeat it as many times as you want. Then we still have a multidimensional image as output, so we flatten it into a one-dimensional vector. It goes through a fully connected dense layer, normal neural network layer, and it has the final output prediction. In this case, it is a classification problem, so we use a Softmax activation. I believe you should have learned this with Suyanya. So, convolutional layer, how does that work? So we're going to, if you look at this image here, we are going to be dissecting this part, and we start with convolution. How does it work? So we have an input image that looks zeros and ones. I simplified it. And it's going to go through a convolution to create something called feature maps. Okay. And to do that, we don't just do a pairwise multiplication, pointwise multiplication like we do in a neural network. We actually do convolution using filters or kernels. It's another word for filters. Okay. And these kernels or filters, these are what replaces our weights. So we learn how the filter looks like. That is what we need to train. Okay. So how does this convolution operation looks like for a 2D image H and a 2D kernel F? So our filter F and an image H, we have a convolution operator that looks like this. It's basically a multiplication, fairly standard multiplication. I'll go over this in the next slide so it becomes clear. However, there's something that we should take into account here. Actually, so first I should say this is discrete. If you want to do this continuously, you just take the integral, so it becomes the summation over infinite elements. If you do this convolution, whereby you multiply basically the image with the kernel F and you shift the elements, then that's actually not what we're doing. This is what we're doing in the neural network convolutional layer is in fact cross correlation. And the definition of cross correlation, which is often represented with this symbol, is slightly different. The only difference there is the sign here. So the end result is basically that the resulting filters are flipped. That is the only issue. So why do we do cross correlation instead of convolution? Because it makes it more efficient to execute. So there's no reason why we should do this flip action. So we're just doing this cross correlation. Okay. Well, I should note I and J here are, of course, the positions in the resulting image map. Each time the filter shifted to calculate the next point. I will explain this formula. There's nothing as clear to explain it as an example. So let's go over an example. You do not need to memorize these formulas. Okay. Right. So what we have is our input, our filter, and our resulting feature map. Let's take the example. For ease of calculation and for the example, I did not normalize these values, so normally they'd be between 1 and 0, but to make calculation easier to demonstrate convolution, I'm just going to put it like this. Okay. So we have our image and we are using a filter. Now, how do we go about to calculate the convolution? It's basically you take, so you overlay the filter over the original image, and then you calculate the product of each element with each element of the filter. 3 times 1 plus 1 times 1 plus 2 times 1 plus 0 times 0 plus 5 times 0, etc., resulting in the new element in your feature map. Then we shift our overlaid filter or window a little bit, and we do the same thing again. You can calculate it, it should be correct. And we shift it again. Here we have a hop size of 1. Hop size is how much we shifted each time. We can set it to be larger as well. And this would be the resulting feature map. So this is an example of an edge detection kernel or filter. Okay. So this particular filter will do edge detection. Okay. So in case our input image looks like this, okay, one side colored, one side not, and we calculate the convolutions. So we can calculate the convolution of the first element. First we overlay it like this. And we calculate 10 plus 10 plus 10 minus 10 plus 10 will be 0. Okay. Only when we enter the sort of central area will we have values that activate only these and zeros for these. So that means the resulting feature map looks a little bit like this. What does it do? It highlights where the edge is, right? Our input image looked something like this. If we assume that the 0 values are bright, it is an image that is half dark and half white. So if we do edge detection, what do we want to detect? We want to detect and say there is an edge here, which is exactly what this feature map does. Okay. What we're going to see in convolutional neural networks is that automatically all sorts of useful filters are learned, and this is very exciting. So I'll show some examples in a little bit, but if you do face detection, you'll see that there's a filter learned for like curves of the mouth and different types of noses. So that's actually quite nice. And in the shallower layers, we'll see simple filters like edge detection, and the deeper you go, the more complex the filters become, and they become real features of humans, for instance. Okay, right, so that brings us to the feature map or activation map. Okay. When we have this original image, for instance, 3 channels, and we multiply it by a filter, also has channels, then we get one activation map or feature map. There's a few ways that you can call it. Okay. So if you convolve over all spatial locations, for each filter, you will get a different activation map. So if you have 6 filters here, you will get 6 activation maps. Okay. So if we look at ConvNet, basically that is a series of convolutional layers interspersed with activation functions, ReLU activation functions. Note that each time you perform convolution, you slightly decrease the dimensions of the feature map. Okay. Also, depending on the number of filters you use, if you use 6 filters, you have 6 channels here. You use 10 filters, then you have 10 channels here. So the dimensions change a bit. Here's an animation of how the convolutional operation happens if you have 3 channels in your image. So for each time we do our sliding window, we got one element from the convolutional operation. And for each new filter, we get a new layer or channel in our resulting feature map. So here's some examples from typical filters that have actually been learned by convolutional neural networks. You see that there's some edge detection going on and changes between specific colors. So one filter always results in one activation map. Okay. So here's some examples of 5x5 filters which result in these feature activation maps. Okay. More cool examples, as I mentioned, low-level features are edge detection very often. If we go deeper, we see actual outlines of eyes, noses, etc. And if you go really too deep, the deepest parts of your network, you can find real actual faces and very, very clear features. Okay. So in this example, it came from, this is a slide from NVIDIA, this came from an application whereby we had face identification. Okay. So it was trained on 10 to 100 million images, and it had hundreds of layers with 1 billion of parameters. Okay. So let's look at the dimensions of the image or the feature maps within a convolutional neural network. Let's say we have a 7x7 input and we use a 3x3 filter which is overlaid here. If we do a stride of 1, our resulting feature map will be, can you guess? Right, we do 1, 1, 3, 4, 5. So I am guessing 5 by 5. Okay, here goes a 5 by 5 output. Okay, I didn't draw it. So if you have a 7 by 7 input, but you use a stride of 2, meaning your hop size is 2, you have a smaller output, right? This time you jump a bit more and you have a 3 by 3 output. What if you have a stride of 3? Okay, so my overlaid, I jump 3, 1, 2, 3, there, and I jump 3, 1, 2, 3. Oh my goodness, that does not work. So sometimes you run into trouble. And this is why with convolutional neural networks, even if you use a nice fast AI or Keras, you always have to think a little bit about dimensions. So it's important that you can calculate dimensions. Okay. So there's a little formula that you can use, which is basically the input image size n minus the filter size divided by the stride plus 1. Okay. That'll give you the resulting output dimensions. What do we do? So just to show you this this formula, if we have stride 1, 7 minus 3 divided 1 plus 1 equals 5 by 5 output. Remember, 3 by 3 output, and here we don't have an integer number, which causes trouble. Luckily, there is a simple way to deal with this. We can just add some padding or 0 padding around our image, and if we add 1 padding row or all around the image, we can now have a nicely integer output dimension size. Okay. Another reason why you want to add this padding is to preserve your input dimension size. Okay. So let's say if you have if your input is 7 by 7, you have a 3 by 3 filter, stride size 1, your output would become 5 by 5. But if you apply 1 padding, then actually you preserve the input size of 7 by 7. So, where were we in our general overview? We have convolution, and it is followed by ReLU. ReLU, as done or applied in neural networks, it is a nonlinear activation function. Okay, so we see nonlinear activation functions to actually empower the neural network to perform nonlinear operations. So that's one of the strengths. You can't really represent the relationship between an image and this is Sonia, as in face recognition, by a linear line. You need to have some complexity in there. So the way we do that is very popular, and it often performs very well, is ReLU, which basically looks like this. It is 0 until 0, and then it's just x, y is x. Okay. Other possibilities are TAN-H, sigmoid, or there are some other newer options as well. Okay, so experiment which activation function works best in your network. Then, if you look back to the image, we had convolution, we had activation function, and then we have a pooling layer. So pooling is often done to do downsampling to simplify the output of the convolutional layer. So pooling reduces the size of the representation. This is good sometimes if you want to speed up the computation as well as make the detected features a little bit more robust. Okay, so you make things a little bit more vague so you can deal with them better. You have less parameters. Two types of pooling that are very popular: max pooling, average pooling. And a typical shape of the pooling is 2 by 2 or 4 by 4. Okay, if your window becomes too big, you're going to lose a lot of information. Okay, so also non-overlapping windows perform best. So your hop size will typically be the same as your pooling size. Max pooling. So you see here that there's non-overlapping windows. If we do that means for each time we overlap the pooling, we do the pooling window, we calculate one number for each of these things. So max pooling takes the maximum number, average pooling takes the average number, 13 here, 20 here. It's pretty standard. Okay. So this is nothing to learn, no weights to be trained. They only reduce the size by averaging or taking the maximum. There are, however, some hyperparameters that you need to set. What is the pooling size window? What is the stride size? Non-overlapping typically works best, but you never know for your problem. So with a neural network, of course, should be said, always perform some experiments to test your hyperparameter settings. Okay. So how many nodes do you use? Have you tried a huge amount of nodes, ridiculously small amount of nodes, something in between? Try a few values, set up a nice experiment to see what works best. Okay. And then finally, so we had convolution, activation layer, pooling. Finally, we flatten it. After we're done with all the convolutions and we've repeated this, we flatten the layer. Actually, let me just go back to this image here. So we do convolution, repeat that as many times as you want. Then we are at the flatten stage. Okay. Flatten is pretty simple. You just change the shape of the vector. And then finally, we have a fully connected layer. So now we're back to one-dimensional vectors, normal neural network. So typically you add with one or two or more fully connected layers. Okay. It's called a fully connected layer because all of the inputs have connections to all of the nodes. Okay. Just a simple normal neural network. What do you use as your training loss then finally? So you could use, depending on your task here. So remember, it's data science. We shouldn't lose track of what we're trying to do here. Doing image classification. So that means I can use cross entropy loss with a softmax activation. That is often used if you're trying to predict multiple classes. Okay, with one class at a time, but out of multiple classes. Okay. You can use sigmoid cross entropy loss for binary classification. A little bit easier. Or Euclidean loss for if you're doing regression. So for instance, mean squared error. So here's an example, Softmax. What you do in the lab, we'll do some image classification, dogs versus cats. And we use the Softmax function here, which speaks for itself. And we get probabilities for each of the classes. In this case, it's clearly a dog. Usually the cutoff is 0.5, especially with binary classes. Now let's see how this is implemented in PyTorch. This is some code that I extracted from the labs that you'll get this week. But let's zoom in on some of the important bits here. Now, as you know, the input size of the neural network is fixed. So that means that we need to load our images all in the same size. And when you get a data set, you'll very often find that there's images of all sorts of resolutions and sizes. So first thing you'll probably want to do is to resize all of the images. As you'll see here on the first line of code, we can use a transform operator in Torch Vision package that will allow you to do just this. So there is also a very interesting function, which is image folder. An image folder allows us to get the labels of our dataset really conveniently. In this case, in the lab, we'll be classifying dog images versus cat images. An image folder allows us to have a folder which is labeled cat and a folder which is labeled dog, and all of the respective images are in there. So the function image folder just uses the label of the directory in which the images are as a classification label. And while you're loading this image folder, you can actually apply the transformation that you defined above. So in the transformation, what we do really is we resize the images into one fixed size, and we'll make sure that they're stored as a tensor. Now, PyTorch and many of the other packages have something called a data loader. Now, a data loader is very convenient, especially if you're working with huge data sets that are stored on a server. A data loader pretty much allows you to load data for your batch. Now, you're not gonna, if you're training on 1 million images, you're not going to load all 1 million images on your computer and process them all at once. You can't do that, especially not if they're stored remotely. So what you're going to do is you're going to train in batches. You'll have a batch size, and each time you train a batch, you're going to load, I don't know, 500 images or whatever, depending on the memory that's available in your GPU. Other things that data loaders allow us to do is to shuffle the data. So basically sample 500 images at random from the dataset. You might also do things like stratified sampling. Let's say we only have 10 images of cats and we have 100 images of dogs. We can make sure that the data loader upsamples the number of the underrepresented class. So that means that if our batch size is 50, it'll pick 25 images of cats and 25 images of dogs. That means there will be duplicate images for one of the classes, but it's called like stratified sampling. Anyway, lots of things to be done with the data loaders, and if you notice that your model trains slowly later in the project, it might be due to the data loader. The data loader, if it's written efficiently, is going to save you a lot of time. Right, so once we've loaded the data, then we will build a sequential model. Basically means all the layers are stacked like the image that we just saw. So each CNN section usually contains a convolution layer, an activation function like ReLU, and a pooling layer. So these are the building blocks, and we've seen them repeated multiple times, but often these elements are present. So what we do is we use sequential to say that they'll come one after the other, and we use conv2d, ReLU, and maxpool2d. Okay. The arguments here are pretty self-explanatory. Maxpool2d means use a pooling of a 2x2 window. Convolution 2d input arguments, three channels, and then 32, which is the output channel. So that means we'll be applying 32 filters of size 3, the last argument. Now, obviously, our model is going to have more layers, so you can easily extend the network with the code at the bottom here. All right, so it's not just convolutional layers. Usually, as we've just seen in the example, we flatten the output and then we feed it into a fully connected layer. But to do that, we need to know what size our fully connected layer should be. And we can use the definition and the formulas that we see in the slides today, but if you're programming, you might equally use a trick, and that's basically you define your whole model here on the code on the left, and then at the end you can basically just output the shape of your resulting vector, and that will tell you the input size that you need to feed when you initialize your linear, meaning fully connected layer of your network. So how is it typically going to be? You'll have your fully connected blocks, fully connected, fully connected, fully connected, and then you flatten it. If you see the code on the right, you flatten it, you add fully connected layers. Here we add 2, we add some dropout, and since it's a classification problem, we end with a sigmoid layer. Okay. We'll see all of this code more in detail in the lab, so don't worry if this is a little bit too quick for all of you. Right, as you see, for the final activation layer, it depends on your problem. So we're doing classification here, then we use something like BCE loss, binary cross entropy loss, because we have 2 classes here. If you have a regression problem, meaning you're predicting a number, then you'd use mean square error or something similar like we've seen. Another thing that you need to do, of course, is during the training, and I'm not going to go into the training loop in detail because you've seen this in previous classes, and it's pretty much the same once you've written a training loop. You use an optimizer. In this case, in the lab, I found that the RMS prop works very well. I'm not going to go into optimizers in detail in this course. We will see it in the AI course. If you're interested, that's where it'll pop up. Finally, use the summary function if you want to see how your model looks like, what are the sizes of each layer, and also how many parameters are trainable. And very interesting here, if you look at the number of parameters, see how small the numbers are for the convolutional layers and see how big they are for the final fully connected or linear layers. So it's really true that convolutional neural networks are much, much more efficient because simply they have less parameters to train and they can capture the information better with these fewer parameters. All right, so as I said, I am not going to go into the training loop, but just like normal, we can make sure that we save the data during training so that we can print it out in our nice graphs to understand what goes wrong. So these graphs, I think they're very important to look at because it gives you some insight into potential overfitting, underfitting, and the likes. Now, we want to perform actual tasks. We want to get results and be able to leverage what exists to get results fast and efficiently. So that's why I want to go over some famous pre-built networks with you. As a data scientist, you'll probably be using some very high-level software like FastAI or Keras, and you just want to load pre-trained networks, okay, and do something which we refer to as transfer learning. More on transfer learning in a little bit. Okay, what is the network that revolutionized this field of computer vision? First, we have Lynette in 1998. Lynette, remember the Le here, that refers to Jan LeCun, our Facebook chief AI scientist. And it was developed on the MNIST dataset. I'm sure you've seen this dataset before, but it is basically handwritten digits that were gathered from the US Post Office for automatic sorting of zip postal codes. Okay, so this small network took as input a 32 by 32 image, tiny sized image, did some convolution, did some pooling, which we call subsampling here. It's some sort of average pooling with some learnable weights per feature map. Don't worry about the details about that. Another convolution, pooling, fully connected layer, and then some Gaussian final output prediction. Number of parameters, 60,000. Keep that in mind as a reference to the other networks. It actually worked pretty well on this dataset MNIST, which we'll go into details later on. LexNet, we're skipping a few years in time here. We're going to 2012. This is 14 years further in time. When we're noticing the emergence of deep learning. LexNet is basically a considerably larger architecture than the original Lynette. However, the architecture is very similar. Sorry. We have pooling, convolution, pooling, max pooling, convolution, etc. It is a lot deeper. It has 7 hidden layers, which was quite revolutionary for the time. Now it's like 7 layers. Is it a deep neural network? And it has 60 million parameters, which is quite a lot. Okay. So this network was presented in the ImageNet competition, which is sort of the benchmark in computer vision. It has 1.2 million training images of 1,000 classes. And I'll be going over some of these famous CNN networks, all based on the ImageNet competition. They all participated. This competition is sort of the place to bring out and benchmark new CNN architectures. 2 years later, the VGG network, VGG 16, offers an even deeper but simpler variant. It has 16 convolutional layers and it's extremely homogeneous. It's an architecture that performs only 3x3 convolutions followed by 2x2 pooling from the beginning to the end. So at each convolution pooling, basically the image or feature map is cut in half, which you can see here on the image. So each operation cuts it in half because of the 2x2 pooling. The number of parameters is 138 million. For a network that's about more than twice as deep as the LexNet from the previous slide, which had 60 million, it's actually not bad. Okay. The good thing is if in Keras you want to apply this model, it's super easy. Okay. There's these built-in functions that says call model VGG16 and even better, set the weights to the weights that won the ImageNet competition. Amazing, right? So you can just use this as a feature selection on your images. Okay. So if you do something like this, what you basically do is you use a pre-trained network. One step further is if you make these weights not fixed, that means you do transfer learning. You start with pre-trained weights, but then you allow these weights to be retrained or trained further or fine-tuned to your task at hand. That's what we call transfer learning. Okay. Another one. The same year, we have Google Lynette, which is also called Inception. It was also developed for the ImageNet competition by Google, and it performs a series of convolutions at different scales. What does that mean? We have our input image here. And then we say, we're not just going to apply 5 3x3 filters. No, we're going to do one 1x1 filter, 1x1 filter, a 3x3 filter, etc. So different filters of different resolutions. Okay. Then in the end, everything is aggregated again. So if you look at the huge overall network, because this is very deep, we have these things that they call inception cells, whereby the image is split up in different resolution convolutions and the result is aggregated. So these parallel paths that we see here are really, with different receptive field sizes, are really meant to capture sparse patterns of correlations in the stack of feature maps. Okay. ResNet, super famous network, which was the ImageNet competition the year after, is an even more deep network. So it ranges from tens to hundreds of layers. A popular one is ResNet 50, but you have ResNet 100, ResNet 15, etc. as well. So the thing is, does more layers always increase the performance? No, right? After a certain time, you don't have enough data, or the layers just start having a negative effect on the performance because your original image degrades too much, right? Even though we have better parameter initialization techniques now and some techniques like batch norm that allows for deeper networks to converge, these techniques are like for the AI course, let's not worry about this. Deeper networks are often harder to converge, okay? So this degradation problem is solved by using ResNet. ResNet includes something called residual blocks. So in the intermediate layers of a block, it learns a residual function with reference to the block input. This identity function basically passes along the input of at the beginning of the block to the end of the block. and it adds it to that. If we look at the mathematical function, that means that y here is equal to the result of multiple convolutions, which is fx, plus the original input of the residual network. Okay, what's often done, because there is a change of the dimensions when you go through the convolutions, it is scaled up a little bit by a weighing scaling factor. Okay, so don't worry about the mathematics of that too much, but the main idea is that in the residual blocks you have this passing of the identity function and it's added to the output of the block. Okay, so this prohibits you from losing information as you go deeper into the network. Okay, so ResNet is really deep. ResNet 50 has about 25 million parameters. That is not a lot compared to what we've seen before. Okay. Did you remember correctly? VGG 16 has about 160-ish million parameters. Okay, so it's doing really well. And the less parameters you have, the less hard it is to train. Okay. Okay, here in this image, each colored block is basically a series of convolutions of the same dimension. And the feature mapping is periodically downsampled by strided convolution. So if you skip when it was higher, your dimensions of your output feature map go down. And it has an increase in channel depth. So more channels, so more filters to still preserve the time complexity per layer. And then we have all of these skip connections, which basically pass the identity function so that information doesn't go lost. So if we look at this ImageNet competition, ILSVRC, we see the depth of the network. And this basically goes over time, 2010, 11, 12, 13, 14, 14, 50. This is the error, lower the better. This was before the area of deep learning, whereby nobody ever achieved a better error than this over many, many years that the competition was running. All of a sudden, LexNet comes along with 8 layers, achieves almost half of the error rate, which was a very noticeable thing. Then we have the VGG-ish, again cut in half the error rate, Google Lynette, ResNet, etc. Okay, so we're going from shallow to 8 layers, 19, 22, 50 layers with ResNet. Okay. Here again, just different representation. The precision instead of the error rate goes up using deep neural networks a lot. So we have ResNext, which is very much inspired by Inception, but basically they follow a split transform merge paradigm. Okay. So in this, the authors introduced this factor called cardinality, which is basically the number of independent paths that you split into. And we always still pass the identity function. The difference here, though, is that it's not added, but it's depth concatenated. So it's added as another channel to your output instead of just being added to your result. There's also DenseNet. DenseNet, we have dense connections. So the idea is that it may be useful to reference feature maps from earlier in the network. Okay, so very much like ResNet, except you have way more references here. It is a densely connected network over time, okay, or over depth. Okay, again, each layer's feature map is concatenated. So depth concatenated together. It has an even better performance with less complexity, and it's based on the ResNet architecture. So it's based on the ResNet architecture because of this identity connections, which happen way more frequently within the block right now, and they're concatenated versus added together. So one thing that happens is this network tackles the vanishing gradient problem very well. So it allows us to train much deeper networks quite efficiently. Looking at the parameters, it's quite low. For a 100-layer dense net, we only have 0.8 million parameters that need to be trained, which is very, very well. Looking at the ImageNet competition from 2020, we see quite some evolutions. So we have talked about a lot of these networks. Now we have here on the x-axis the number of parameters in millions. So that means the lower, the better. And then we have the accuracy. So here it's the highest, the better. So where you want to be is in the top left corner. And what we see there, while Inception has low parameters, so as ResNet, DenseNet, one that jumps out is EfficientNet. So let's have a little look at EfficientNet, different versions of EfficientNet. So EfficientNet really is based on the principle that we can do different scaling methods within a network. So we can have width scaling, where we change the node. We can have depth scaling or resolution scaling. And what EfficientNet does is compound scaling. So it can be very hard to figure out how to scale your network and set your hyperparameters. Basically, EfficientNet solves this by saying that we need to use one uniformly scaled method. So we do scaling on all different levels using one scaling component or one scaling factor. And it uses a grid search methodology, which we saw in one of the earlier lectures related to SVM, to find the relationship between different scaling dimensions of the baseline network under a fixed resource constraint, which will be your flops or the computing power of your machine. So it'll find an appropriate scaling coefficient for each of the dimensions using grid search. So just to elaborate a little bit about the types of scaling, width scaling basically means the number of channels that you get in your feature maps. Depth scaling will be the number of layers in your network, and resolution scaling basically simply is the number of pixels in your image. So the height and width of your image. So the result is a carefully balanced network depth, width, and resolution, which can lead to a better performance. So we basically call this field automated machine learning, meaning that you learn how to build your model, how your model should look like, what the hyperparameters of your model need to be, using machine learning already. So this new scaling method uniformly scales all the dimensions of depth, width, and resolution using a simple but very efficient compound coefficient. Okay, so it's a very structured scaling. So in the EfficientNet paper, there's not only this new scaling method, there's also a new baseline network proposed, which optimizes both the accuracy and the efficiency in terms of floating points operation per second of your algorithm on your machine. So this is basically consists of MBConv blocks, which is mobile inverted bottleneck convolutions, similar to MobileNet version 2, which I won't go into detail, but it's slightly larger. So how does this MBConv look like? If we look at a normal residual block, it goes from wide to narrow to wide. So the output is scaled back to the input size so that X can be added to it. So in residual blocks, remember that we have the identity function here. So we perform a convolution which typically reduces our input size, but we perform a convolution such that we can get it back to the same size and add it here. In inverted residual blocks, we basically go from narrow to wide to narrow, which is the opposite of the residual block. So it initially takes a low dimensional input and expands it with a 1x1 convolutional layer, followed by a 3x3 depthwise convolution and back to the input shape using a 1x1 convolutional layer so that it can be added added to the identity function. All right, so the resulting efficient net performs extremely well in the ImageNet competition. And these variants B1, B4, B5 are obtained using different scaling coefficients. So the hyperparameter tweaking is important. Okay. So if you want to read a little bit more on all these variants, they change all the time. This is a nice article on Medium that you can refer to. Now let's have a look at the Hello World example from convolutional neural networks, which is based on the MNIST dataset of 100 digits. I mentioned this dataset before. It's gathered in the US Post Office, and it was meant to help automate the sorting based on zip codes. Okay, Jan LeCun created this dataset, and they're 28 by 28 grayscale images with pixel values from 0 to 255. The dataset is 60,000 training examples and 10K test samples. Okay, so quite a small dataset. And the output, obviously, is an integer from 0 to 9, the number. So let's implement Lynette for MNIST. I did this for you, and we did convolution pooling, and then 2 fully connected layers with the binary cross entropy. If I run this, then basically what do I see? I see first that the loss function training, which is the blue line, goes down nice and smooth, which we expect. The validation loss, I used part of the training set to validate, also goes down. However, oh yes, and the accuracy of the validation set goes up. Excellent. Looks good, right? Looks good. I feed it a test image, and what do I get? The prediction probabilities for each class. 2 has the highest probability, so we say it's a 2. 0 also has a high probability, but it's okay. It's still easily to distinguish. So I feed it a bunch of numbers, and let's see, it says it has 96% classification accuracy, but let's have a look. It classifies correctly this one, this one, this one, but these are all misclassified. Any ideas why? Well, let's see. We didn't train on the full data set. So let's take the full data sets. What I did is I trained on a smaller data set to make sure that I could fine tune my architecture a lot and run the model a lot quicker. This is a nice practice to do when you're developing something. On the full data set, I had a look at my filters, just visualize the filters, and it looks like we have some edge detection going on, diagonal detection, point dot detection, etc. If I look at how well the model performs predicting these images, it's not bad, but it's actually not really good. Okay, so we achieve 99% accuracy on our test set, but if we have these unseen images, not from the test set, we get very bad results. Basically, everything is misclassified. You could see how, right? This is predicted as an 8. Sort of resembles it. This is a 2. Same shapes, okay, but performs poorly. Any idea why? Well, the test images were all black background, white foreground. So that is what the model is expecting, and it can deal with numbers that look slightly different, that have different backgrounds. So we can actually fix that. We do data augmentation. So this is something that as a data scientist you always should keep in mind. Is the distribution of the test data set and the training data set the same? Is this what we expect to see in real life? What could be the problems with our data and how could we change it? Okay. So when we have these different backgrounds, it doesn't work well. So one thing we could do is we could invert images. So instead of just having this, be pretty easy to just do really one minus pixel value and we get this white and black one. Let's train it on double the dataset and see how it performs. These are our old results. These are the new results. Amazing. Just the 8 has some trouble with, but that's understandable. We probably have to do some more augmentations to make that work. So, not having labeled data with these backgrounds, with these white backgrounds, still it performs pretty well. So you could do some other augmentations, maybe adding some color in your dataset. And that might increase the performance, so this one is also correctly classified. Okay. So how does data augmentation really work? Here's an example from our lab. We see that when we have images, we can actually do a lot more things than just color them. We can rotate them, flip them, mirror them, do a cut-off part of the image and transform it. We could squeeze the image, etc. We could scale it up or down, and we'll see many examples of this. But the cool thing is that we can again use this transforms function, and the transforms is basically called along with the data loader. So in it, this data loader is very, very important. And along with just shuffling your data or doing stratified sampling or something, you can equally say like select 50 images and apply some random transforms on the dataset. And we'll try this in the lab. So we'll first train a normal cat versus dog image classifier, and then we'll augment the data. And you'll see how the performance changes. Will it augment? Will it decrease? I think it's pretty clear it'll increase the performance, but it's up to you to find out in the lab. All right, if you want some extra tips, check out this article, Bag of Trips or Image Classification with CNNs, to get some more pointers. So I've been talking a lot about images, but is convolution only for images? No, it is not. Okay. So while image processing has really been the thing that's made CNNs popular, anything that deals with multidimensional matrices can be used for convolutional neural networks. So the data does not even need to be 2D, it can be applied to 1D or multidimensional data as well. For instance, video, word vectors, text processing, or even audio tasks, which is what I do in my lab. So let's have a look at audio, since it's the most interesting application. So data analytics are or is important for audio. What we did, some of the research we did is spoofing detection. So how, if you have a voice authentication system on your in your home that identifies you based on your voice, sort of like Face ID on your iPhone, but using your voice. We develop algorithms that can detect if somebody has recorded your voice instead of it being a real voice. We can do music genre classification, spoken word detection, which word are you saying? We can do hit prediction, speaker identification, who is talking if you know the voices of 20 people. We can do emotion detection from your voice or from music. Does it sound sad or happy? All of the stuff we've been doing with the Amai lab. If you're interested in our work, check out the website and look for Amai. So how do we start on this? Well, we can represent audio as an image, for instance. It is a waveform. Waveform is basically a series of numbers. But it can be more informative if we use spectrograms. These are two main approaches. Although there's been some convolutional-based neural networks that represent waveforms very well, which I'll talk about. The easiest way would be to represent sound as spectrograms, basically a visual representation of the spectrum of frequencies of the sound. So for every bin, so for every time, this is the evolution of the signal, we have frequency bins, and the color will denote the intensity of that particular frequency. So here we know that something with a low frequency is being said. Okay. So to get these spectrograms, usually you have to do some Fourier analysis, and it gives you the distribution of power into the different frequency components on the y-axis. Okay. So this is not a signal processing course. If you're interested to learn more about this, you can always approach me though. But given that we can have the spectrogram, we can then feed it into the neural network. Now we should note that there are different types of spectrograms, and one that I want to point out is the MEL spectrogram. Because this MEL spectrogram basically has the frequency bins rescaled to emphasize the frequencies that the human hearing can learn, right? Can hear. So that's why very often these MEL spectrograms perform better. Because if we're speaking, we're doing speech identification, it makes sense that a spectrogram emphasizes the tones that we hear best. Okay. If you're interested to include some spectrograms in your neural network, you should check out my student Raven's library NN Audio, which basically leverages neural networks to calculate spectrograms. So this is a little bit too deep for this class, but if you are to represent the Fourier analysis as a transformation that happens within a neural network node, you can actually leverage a GPU for spectrogram calculation, and calculating this spectrogram becomes the first layer of your neural network. So you can just feed it audio files instead of the images. Okay. So he uses one-dimensional convolution to calculate the actual spectrogram. That being said, once you have the spectrogram, you can just feed it into a convolutional neural network, and it has been done for things like genre classification, audio simulation, similarity measures, etc., etc. Okay. So in this slide, I still have LibRosa in here, which has a simple MEL spectrogram function. You can, even if you're using Keras, you can use NN Audio to get a similar .spectrogram function to get the spectrogram out of here. Just check out the GitHub, there's very nice tutorials on there. So once you have the spectrograms, you can use it for speech recognition. For instance, in a study done by Abdelhamid in 2014, they have spectrogram input, then different convolutional layers, max pooling, fully connected layers, to identify which word is being said. Okay. So then the network is identified using something called the word error rate, and the network itself has one convolution, two fully connected layers, etc., etc., and they compare it to a deep neural network when it outperforms it, especially if they use pre-training, so pre-trained neural networks. There's music emotion classification, also done by spectrogram. You have your audio here, convolution, pooling, etc., etc. Here we use 4 convolutional layers, and it just can predict 18 different emotion tags. Now, if you want to represent audio in a slightly different way, also based on spectrograms, you can use pre-trained neural networks, just like the pre-trained neural networks from the ImageNet competition, like you get ResNet 50 based on ImageNet. You can get VGG pre-trained on AudioSet. AudioSet is a huge data set released by Google, which is basically has about 1 million images of 1,000 different classes or something. I forget the exact number, I'm sorry. Maybe I can display it for you here. And the VGG-ish model basically provides 128 dimensional embedding for audio based on a pre-trained model using the AudioSet dataset. Okay, so it's sort of like word embeddings. You feed it a word, you get a word-to-vec embedding. You feed it an audio file, you get a VGG embedding. Okay. So this particular VGG is a variant using 11 layers, and the changes that they made was they changed the input size to fit a log MEL spectrogram audio file. It dropped also the last group of convolutional and max pool layers, so they now have 4 groups of convolution and max pooling layers instead of 5. Instead of 1,000 white fully connected layer at the end, they use 128 white fully connected layer that can act as the embedding layer. you can download it here. It's very easy to load it into your network. So we've seen one possible way of representing audio using a spectrogram and then possibly a pre-trained deep neural network to represent that spectrogram. Now let's have a look at the other possibilities of using the waveform instead of the spectrogram. Now first, to do this, let me talk about a recent invention or a recent novel architecture called the temporal convolutional neural network, which is basically a convolutional neural network made for time series. The TCN can take a series of any length and output it as the same length. Okay. But the output at length t is only convolved with elements that occurred before t through something that they call dilated convolutions. This is a one-dimensional convolution, okay, typically, in its most basic form. So we have as input a time series here, and so we have time 1, 2, 3, 4, etc. And at time t, the convolution takes into account some previous elements in time, never elements that occur later in time. So these dilated convolutions are set up in a hierarchical way. So they get joined later on, the output. So this is a very, this is actually bigger, like this. So this is an interesting hierarchical way of doing convolutions over time. So with this knowledge of TCNs, which often occurs in a decoder and an encoder path, that's the original TCN, we can look at something called a WaveNet. WaveNet is meant to take into account relationships between waveforms, so audio files, that occur on different hierarchical levels. So we can see patterns here at a very deep level and patterns at a very zoomed out level. So this WaveNet, because it's based on temporal convolutional neural networks and these dilated hierarchical convolutions, allows you to take this into account. There's been some very cool results using WaveNet. Okay. So it does predictions in this way. By doing convolutions, each element with the previous elements, then joined together in a hierarchical way on a larger level. Okay, this is a bit of a challenge. Okay, right. So this is how WaveNet works. In addition, the difference with a temporal convolutional neural network is that WaveNet, in addition, this is not shown on the blog, but in the GIF, but they also has residual connections. So the identity matrix is also passed along at certain points, so that you actually sometimes you keep the original image and you don't lose the information. That means you can go deep a lot easier. They also have gated activations, which is something that you see in the LSTM course. It helps to fight the vanishing gradient problem. So again, you can go deeper without risking that your training process is impaired because your gradient gets too small. This is a small detail. Yeah. So WaveNet, a very powerful tool to read in your data. Again, you can just load the WaveNet model or WaveNet architecture, and it can be used to represent your audio data. Okay. Some of the research I've done in my lab is a very recent paper from my PhD student Tao, who created Attend EffectNet, which is basically doing multimodal emotion classification. And just to show you that you can use these pre-trained features as different multimodal inputs. So again, we're doing data science here, so we don't really want to go into VGG-ish or we want to go into WaveNet and try to improve the network. You can just leverage it. It's sort of like using libraries to load your data. You can equally just use a library like she did. She had movie clips and she wanted to predict the emotion of the movie clip. We have audio and video and emotion, so she used the OpenSmile library to get frequency spectrogram-based features, not neural network related. Then she used VGG-ish, pre-trained on audio set to get features. Video, she used ResNet 60, ResNet 50 pre-trained on ImageNet. And then she used i3D network as well, which is more scene detection. So then she used FlowNet to get motion features. Oh, i3D also action recognition. Okay. So using all these different features, she then fed it into self-attention transformer network, which I think you'll see in one of the next classes. Self-attention, basically, she attended the network, so she told the transformer network to try to learn which feature to pay most attention to. And it turns out that the audio features have most influence on emotion. Okay. You might think that in a movie the video influences us more, but actually the audio features have most influence. We're doing some tests now, adding a third component, which is text, and we'll see how that goes. This is still research being done right now. Okay, so the Attent Effect Net does predictions. We have the, which is it? The prediction is the dotted blue line, and the ground truth throughout the movie is the valence, positivity, negativity of the sentiment, and the arousal, the energy of the sentiment. So you see that it's not bad, and it follows the overall trend. Okay. If we do the comparison of how it actually works, this model compared to other models, we see that in terms of mean squared error, for instance, our feature Attend Effect Net, this one, has a quite low mean squared error in terms of arousal and valence. If we compare to the model with using only audio features only model performs pretty well on its own. The model using only video features doesn't perform quite as well. Okay, so again, emphasizing the importance of audio on emotions. Okay, you can ignore these for now. This is some state of the art that we compared with, that we outperformed in terms of valence. This is table 2 shows a different data set, which basically confirms pretty much our results. If you're interested in the paper, check it out. It's on my website. All right, that's it for this week's class. I hope you enjoyed it. In the lab that's to come, we're going to be experimenting with how we can implement convolutional neural networks, train them from scratch, and how we can leverage pre-trained convolutional neural networks. Right, hope you enjoyed the lecture. If you have any questions, be in touch with me. I'm very happy to help you. All right, see you in class.